Hey everyone, Katrina here, and today we're going to talk about what are polynomials. Be sure to subscribe for more videos like these and watch to the end to see all the examples. Okay, so if you're in grade 11 math or grade 12 math, and maybe even grade 10, you might start hearing this word about polynomials. So today we're going to dive in and really understand, well, what is a polynomial? What is it made up of? And then we're going to start to talk about some of the properties that make it such an important and exciting function in mathematics. So first of all, let's discuss, well, what is a polynomial made up of? So essentially, a polynomial is a function that is made up of the following three components. So first, it contains variables. So oftentimes we'll use the variable x as our independent variable. And then secondly, it's made up of something called coefficients. So coefficients are some constant that you have multiplied in front of your variable. So for example, we might have some coefficient k, and then that is found in front of our variable x. And in this case, it's important that our coefficients here are a constant value. So they're not a variable themselves. And the third thing that polynomials can be made up of are constant terms. So let's write that out. So when I say constant terms, I'm not talking about the constant that we have over here that's multiplied in front of our variable, but I'm talking about a separate constant term that's found independently kind of at the end of the polynomial. For example, if you have some plus c value at the end of your polynomial, that would be our constant term. So now that we have this generic thing that polynomials are made up of, let's look at the exact, precise mathematical definition of the polynomial. So let's write that out right over here. So here is the generic form of a polynomial. We can write it in function notation such that we have f of x. This basically means that f here, this is our dependent variable, and x is our independent variable. So let's just write that out. So f is dependent, x is independent. So that means that we are feeding different values of x into our function, and every time we give a different value for x, we're going to get a different value for f. F depends on x. That's how you can understand it. Okay, so now that we have that cleared up, let's write out this full definition. So we have f of x equals to a, which is a constant, x to the power of n, where n is our exponent, plus b, another constant, another coefficient, I should say, multiplied by n to the x to the power of -1, and then plus c, x to the power of n minus 2, and then we write this in a general form, so we keep on going until we have some value of x plus some value of c. So maybe we'll change this up here. We'll write this as, let's choose another variable. Let's say g, as just some constant at the end that we are adding. Okay, so if I were to go look over here, let's analyze everything that's going on. So these values that I'm highlighting right now, these are our coefficients. So when I talked about our coefficients, our number 2 that we have over here, that's what's going on. So there's some constant coefficient that's multiplied with our variable. And then next, we can see that we have our variable x over here. So this is what we discussed in our first component over here. So that is our independent variable x. And then lastly, we have our final constant term that we can see at the end over here, our g, which I end up writing as c over here. These are just variables, so they can be interchangeable. Essentially what that means is that is just a constant value that you have at the end of the function that's not multiplied with any other variable, just on its own. Okay, so the last thing that we haven't talked about yet is n. So what is our n value over here? So what is n? So n is, oh, sorry about that. So n is our exponent. So what values is n allowed to take? So that's what we're going to look at right over here. So n is actually going to be defined that n has to be greater or equal to 0. You can also write this as n-e-w in fancy math notation, meaning that n has to be greater than 0 and it has to be a whole number. So that means it can't be like 1.5, it has to be like 0. In this case, it can be 0, 1, 2, 3. So we can write that out. 0, 1, 2, 3, all the way forward. So those are the values that we can take for n. And this is important because this allows our f of x to be a polynomial. So all these conditions have to be met. So let's look at a few other properties that we have for a polynomial. So now we understand what they can be made up of, and we understand what the generic form looks like, but we have to discuss a few other housekeeping properties here. So let's write down some key features to our polynomials. So first of all, how do we decide which order to write it in? So it's important that it is written in descending order. So when you write something in descending order, that means that you go from the largest order to the smallest order. So we're writing it in the it's written in descending order of x. So just like we saw over here that I'm pointing to in our first notation that we wrote, we start with our n value, and then we do n minus 1, n minus 2, and then when we get to x over here, so this means that we have n equals to 1, and then technically our last term can be written as g times x to the power of 0. So we can see how we went from n to n minus 1 to n minus 2, all the way to n equals to 1, and then n equals to 0. So we go from largest to smallest in descending order. And that is the proper way how to write out polynomials. Okay, so that's one key feature. Let's look at our next key feature that we have. So the next one is the degree of the polynomial. So when you see a polynomial, how do you establish the degree? Because in mathematics, a big discussion is, oh, I have a polynomial of degree 5, I have a polynomial of degree 2, and that can actually impact some of its other properties. So how do you determine the degree? So the degree of the polynomial is the following. So it is actually going to be the value of the largest exponent. So value of the largest exponent. So what are our exponents? Remember that our exponents, these are our n values. So whichever the largest one is, that's going to be the degree of our polynomial. The other way how we write it sometimes is we call it the greatest power of x. Greatest power of x. So what is the biggest one? So let's look at a little example over here. So here we're going to show an example that makes sure that we abide by both the first and the second key feature. So let's write a polynomial f of x equals to 3x to the 7 plus x to the 4 minus 5. So in this case, we're following the first the first key feature, where we're doing it from descending order of x, the degree of x. And secondly, let's determine what is the degree of this. Well, in this case, we have to look at all the exponents, all of the n values. So here we have n equals to 7. Here we have n equals to 4. And next to our constant, we have n equals to 0. Because like I said before, it's the same as multiplying our constant 5 by x to the power of 0. Okay, so we look for our biggest one. We can see right away that 7 is going to be our greatest power of x. So we would write then, therefore, we would say the degree of f of x is 7. Okay, so that is 2 main features, and then I'm going to show you one more feature here, and I guess it's something that we should all know. It's another lingo that people may use. So you would say, oh, I have a polynomial of degree 5, and then you'd say you have a leading coefficient of a certain value. So that's what we're going to talk about. So we're going to talk about leading coefficients next. So we mentioned that coefficients is something that we have to have when we have a polynomial, right? If we go back over here, that was our second thing that our function is made up of, a coefficient, which is a constant that is being multiplied in front of our variable. So all polynomials have a leading coefficient. So what is a leading coefficient? So a leading coefficient is simply the coefficient that is in front of the term containing the highest power of x. So coefficient that is in front of the term containing the highest power of x. That way you have it all written down. So what does that mean? So if we look at our previous example that we stated up here, we said that our highest power of x, or greatest power of x, is n equals to 7. So that means that our leading coefficient is going to be the coefficient that is in front of that term. So in this case, we see that the 3 is our coefficient in front of this. So that means that therefore 3 is the leading coefficient, which I'm going to write as LC. So when you discuss polynomials, you'll talk about its degree, and you often also talk about the leading coefficient. Along with the leading coefficient, so there's 2 things we have to think about. So part A is the coefficient that's in front of the highest power, and part B is looking at the sign of the leading coefficient. So when I say sign, that means, is my leading coefficient positive or is my leading coefficient negative? Because the sign is very important when we talk about end behavior of polynomials. So therefore, when we talk about leading coefficients, we have to think about 2 things. We have to think about what is the value and also what is the sign. Okay, so now you have these aspects. You can talk about the degree of the polynomial, and you can also talk about the leading coefficient and its sign. So now we're going to go into just a couple small examples, looking at some polynomials and practicing determining what is the leading coefficient and what is the degree and the sign. So first of all, let's just look at polynomials versus not polynomials. So we'll say poly versus not poly. So this is just back to the beginning. What is a polynomial versus what isn't? So here are some examples. Y equals to x, y equals to x squared minus 2x plus 1, and let's say y equals to negative 5x to the 5 over 4. Not polynomials. What do we have? Y equals to sine x, y equals to 2 to the power of x, y equals to 1 over x. Okay, that was a lot of information. Let's talk about why these are polynomials versus not polynomials. So first of all, let's look at this example here. We have y equals to x. Well, we have a variable, we have a coefficient, and we don't have a constant term, but that's fine. Nothing, I guess, goes against our definition. So this one is good. The second one here, again, we have variables, we have big thing is n is greater or equal to 0, and we also have our constant term over here. So we're good. Last one over here, we do have a coefficient over here, -5. It's okay to have a fractional, like a rational coefficient. So here our coefficient is -5/4 times x to the power 5. That is okay. We have a number, it's rational, that's totally allowed. It's still a coefficient, and that's fine. The coefficient in this case does not vary, so it's a constant coefficient, which is important for a definition. And we see that we have another power of n, which is also greater or equal to 5, greater or equal to 0, and it is a whole number. Looking at a non-polynomial side, sine is not a polynomial. In this case, it doesn't abide by all the rules of our polynomial. It doesn't follow that same structure of coefficient x to the power of n. So in this case, it is not a polynomial. We can't have x embedded in other functions, and that goes against the definition of polynomial. If we look at the second example here, we have x up in the exponent. That is not allowed for polynomials. In polynomials, x has to be the base. We cannot have it in the exponent. So therefore, this is also not a polynomial. And here, y equals to 1/x. Well, that can be rewritten as x to the power of -1 following exponent rules. And what do we have there? An exponent that's negative. That means that n is less than 0. So that breaks our rule that n has to be greater or equal to 0. So those are some cases where it's not a polynomial. So pretty much a polynomial just has to follow that standard form that we talked about. It has to be in that ax to the n plus bx to the n minus 1 all the way to x plus some constant k. It has to be in this format. It's okay, these values can be plus or minus as we go along. That's okay, but x has to remain as the base and n has to be a whole number and greater or equal to 0. So we're going to do one more example here where we try to find the degree and the leading coefficient. So let's say we have f of x equals to -7x3 plus 5x squared minus 10x minus 29. So in this case, we want to ask two questions. What is the degree? And what is the leading coefficient? And what is the sign of the leading coefficient? Okay, so let's do this one by one. So first of all, the degree. We said that the degree is the largest exponent or greatest power of x. So let's go through all our options. Here n equals to 3, n equals to 2, n equals to 1, n equals to 0. This is also following the rule that it should go in decreasing order of x. So technically, if it's always in correct order, you can grab your degree from the first term of x. So therefore, our degree here equals to 3. Our leading coefficient, well, that's just the coefficient that's stuck to our term of x that has the largest degree. So our leading coefficient is -7. And here we can obviously see that the sign is negative. So we have a third degree, we have a leading coefficient -7 and a negative sign. And our polynomial is written in the correct form in decreasing order from largest power of x to smallest power of x. So you can see here that we don't order it by the size of our leading coefficient. It is purely ordered on the degree of x. That has the priority when we write out our polynomials. Yeah, so I hope this was a very good intro to polynomials for you. Now you can feel confident knowing what polynomials are, and you can also identify key features of polynomials, and you know how to write them out correctly. There will be more videos to come on learning about the end behavior of polynomials and other properties coming up, so stay tuned. Be sure to subscribe for more videos like this, and I look forward to seeing you next time.